Good evening, everyone. This is Travis Walter and Dan Pearson's presentation on our final project for the winter quarter. The project we worked on was from drivendata.org. There was one of three power laws projects that have recently been posted, and the one we decided to work on was the detecting anomalies in usage. So this problem was posed to identify methods to detect abnormal energy consumption. Data from multiple sites across multiple geographies are provided, with the ultimate goal being to identify anomalies in the data set, with the catch and the real challenge that there's no labeled data. So we had to build models to identify the outliers ourselves. This is an overview of the data provided. It was quite large, 40-something million rows, I believe, much larger than anything I've ever worked with. But there's consumption values, which was by meter ID. There was 187 meters provided, I think. Timestamp, which is they were taken every 15 minutes, or every 30 minutes, every 15 minutes, depending on the meter. The values, the reading from the meter itself. The building metadata, so there was the meter ID, the site ID, which is which building it came from, description, and various other aspects. There was some weather data provided, which was just temperature, but provided at different intervals throughout the time course, and then some information on holidays. So we viewed this as sort of days off when buildings wouldn't be as occupied. We're going to go through these analysis steps and kind of what we did for this project, and I'm going to start with the cleaning and prepping of the data and some brief exploratory analysis. So for the data prep, this was a challenge for me to put together in terms of visualization. This data set being so large, so I just want to sort of walk through kind of how we approach this. We were able to merge all of the information by unique identifiers, at least one in each data frame provided. So that was a challenge, but the join functions from the tidyverse or the data table package were really great for this. The submission file, which we'll reference to at some point as the test set, actually only had 3 of the 187 meters. This was sort of peculiar, but we're gonna take advantage of this, and I'll go through a little bit more later. KNN imputation was used for missing temperature values. We did not impute any of the other values for the actual meter readings. We don't want to introduce any bias if the goal of this is to be predicting or finding anomalies. Imputing based on nearest neighbors and such, we just felt could have thrown that off drastically. And the temperature values, we decided instead of keeping them every 15 minutes, we just averaged every reading from each station that was provided by hour. So temperature were just averaged to shrink that a little bit. So after that was all done, the final combined data frame was about 44 million rows by 9 columns. As we were exploring this thing, and as I mentioned, when we decided to remove the missing values, one of the main drivers for that was when we started really looking at the test set versus the train set and the meters that were provided in each. And it was quite convenient, and we found out eventually that once you remove the missing values from the meters that were in the test set, what you're left with is the actual test set. So the organizers did not include any missing value readings in the actual test set, which was a bit of a relief. So using that information, that was the real deciding factor for us to say if the meter reading was missing, we just would delete it. That way it didn't introduce any bias into the anomaly detection, and also it was able to sort of shrink down and get more in line with the test set. And also because of that, we decided that sort of from a perspective of, what is this problem truly asking, or what did we feel like we were really working on. We actually decided just to focus our modeling on these 3 meters that were in the test set. We didn't feel that building any predictive models for any of the other meters would have benefited us in finding this data. Now, in hindsight, maybe we could have used some of those as a feature instead of an actual predictor or a dependent variables. But this is how we approach the problem. So we from going forward, we will focus only on the 3 meters that were in the test set. So quick, brief EDA before I turn it over to Dan in our for the modeling that we did. This is just the series for one of the meters, 234, 203. Bounces around a lot, but it seems to be fairly consistent, other than that sort of chunk there in about the early third. That tall red line, maybe that's one anomaly right off the bat that's just got a flag there waiting for us to an easy one to call. This is the second meter, 33461. This one is has an apparent seasonality to it. We'll have to dig deeper and find out if the peaks and valleys were months or seasons or what those are. But we should be able to turn this into a more of a typical supervised learning set, in the sense that, break apart the timestamp into the components. This was an interesting one. This one is the 389686. We stared at this for a little bit, trying to figure out what was going on, if that was just a yearly cumulative consumption. It wasn't the case. It was unclear exactly what the breakpoints were until we looked at the discussion board, and somebody astutely pointed out that it was nothing more than every time the meter hit 1 million, it just reset. So it would climb up, hit 1 million, reset, keep counting. And that this allowed us to focus on the differences. Once you difference these values, then you can actually get a nice reasonable set, which is what this shows here. This is more representative of a time series type data set that we've all seen. And again, it shows some nice big spikes that could be anomalies, and even some that are sort of below the majority, which are also something we considered. And just to confirm to ourselves that this was in fact a reasonable thing to do difference, when you did the cumulative sum of the whole thing, you actually see here a nice straight line. That that was in fact the resetting at 1 million, and it was date independent. So from a feature engineering perspective, we focused a lot on the timestamp, removing the day of the week, hour, month, that sort of thing, AM and PM. This is just a plot showing the temperature over time, and then colored by if it was in the AM or the PM part of the day. Pretty consistent. We felt okay when we imputed this that it wouldn't throw it off too much. This is just an example. This is the week of the year, so the year was broken up into 52 weeks. Again, this is that seasonality meter where there was the clear spikes in some sort of season, and this starts to suggest now that the summer months are high demand, so possibly an air conditioning type meter, maybe if there's an air conditioner running, or if it's in the southern hemisphere, I suppose there could be the heater if it's winter down there. But either way, the demand seems to be quite high during the middle part of the year. And then this is the hour of the day. So again, broken up by, colored by AM and PM, but also just to show sort of, so we can see if it was like a shift, like a work shift effect. And yet it does appear to be the case, where maybe between 7, 8 o'clock till maybe 10 o'clock or so that is the peak demand. And so these are the approaches. These are the sort of plots. We made many of these plots. I could talk for a long time about them. This is sort of the approach Dan and I took to breaking this apart, trying to get an idea of what was going on with these meters, and maybe try to help. We could look at the values on the y-axis and kind of get an idea of maybe where some of the outliers may fall. Again, on this plot, you can see some at the bottom that maybe they're that low. That could be an indicator where the majority of them are all sort of a little bit higher, and some of the ones that spike up. So he's going to go through next the different models we built and some of the results that we got from those.